Okay, 3.36 is actually the second problem out of like the past four that we've done that is once again going to require contour integration and knowledge of the Cauchy integral theorem, or the residual theorem. Originally, like 2 problems ago when we first ran into this, I recommended that you just plug this into like an integral calculator online. That was because I assumed that Calculus 3 techniques would only come into play after Chapter 3. Evidently, it looks like they're actually going to start coming into play near the end of Chapter 3 when we're doing these end-of-chapter problems. So given that, I've decided that it is probably worth it to just go over briefly Cauchy integrals and contour integration and all that stuff. But that's going to be for later in this part number. Part A doesn't actually require it, so we're going to go immediately and start off with part A and say, okay, we have a wave function. We want to normalize it to determine A, so that's pretty easy, right? We just enforce that 1 is equal to the integral from negative infinity to infinity of magnitude psi of x comma 0 squared dx. And now there's no imaginaries here, so it's just a simple matter of taking the squared. 1 is equal to a squared integral from negative infinity to positive infinity of 1 over x squared plus a squared squared dx. And this should immediately sort of imply that you should be using trigonometric substitution. If you don't know what that is, maybe go back and look it up and try to figure out how to do it. Trigonometric substitution basically tells you that anytime you encounter something that looks like 1 over x squared plus a squared, or 1 over square root x squared plus a squared, or anything like that, there are a set of substitutions you can use, which can then sort of back convert this equation into something that's purely a sinusoid, which is significantly easier to actually do an integral for. In this case, if you have something like 1 over x squared plus a squared, immediately you should be trying the following substitution of x equals a tangent of theta. In this case, dx is going to equal a times secant squared theta d theta. And then, if I then take this and I plug it into my x squared plus a squared expression, this is going to give me a squared tangent squared theta plus a squared, which is equal to a squared tangent squared theta plus 1. And that's a trig identity, right? That's just equal to secant squared theta. So in that case, if I plug this back in here, I now have 1 is equal to a squared times the integral from negative infinity to infinity of 1 over a squared secant squared theta squared dx. Okay, now I want to convert this from a x integral into a theta integral. So I'm going to convert this. Dx is now going to change into a secant squared theta d theta. And if x is going from negative infinity to positive infinity, well, we just defined here that, let's write this in red, x equals a tangent of theta, right? So if x goes to infinity is equal to a tangent of theta, or plus minus infinity is equal to a tangent of theta. Tangent, well, this is a constant, so you can just sort of divide it over and it gets absorbed into the infinity, which implies that theta has to equal inverse tangent of plus minus infinity for your integral bounds. So if you plug that in here, this is going to give you tangent inverse negative infinity to tangent inverse positive infinity. And that just is going to evaluate to negative pi half and positive pi half. So let's rewrite this. 1 is equal to a squared integral negative pi half to positive pi half 1 over a squared secant squared theta squared times a secant squared theta d theta. Okay, now let's do some cancellation. A secant squared theta divided by a fourth secant fourth theta, right? This is going to equal, the a is going to cancel out the bottom, secant squared is going to cancel out with the bottom. This is going to give you 1 over a cubed secant squared theta. Okay, writing this out fully now, our normalization condition is now 1 is equal to a squared integral from negative pi half to pi half of 1 over a cubed secant squared theta d theta. Now keep in mind that cosine is just 1 over secant, and secant is 1 over cosine. Secant and cosine are reciprocals of one another. So 1 is equal to a squared over a cubed times the integral from negative pi half to positive pi half of cosine squared theta, d theta. And at that point, I mean, we can just solve this using double angle, right? So we know that, for example, cosine of 2x is equal to 2 cosine squared x minus 1, in which case cosine squared of x is going to equal 1/2 of cosine 2x plus 1. So if we plug that in, we now have, where did my mouse go? Oh, there we go, sorry. We're now going to get that 1 is equal to a squared over a cubed, integral from negative pi half to pi half of 1/2 1 plus cosine of 2 theta. Close this off with a d theta, and now you have two integrals, right? Let's multiply the 2 out to this side. So we have the 2 at the front now, and now you have 1 equals 2a squared over a cubed. Now doing this actual integral, right, we're going to get theta plus 1/2 sine 2 theta. Is that right? Cosine 2 theta times 2. Yeah, that's correct. Evaluated from negative pi half to pi half. Okay, well, sine of 2 times pi half is going to be pi, and sine of 2 times negative pi half is negative pi. Sine of pi is going to equal sine of negative pi, because they both equal 0. So this entire term here goes away. What you're left with is pi half minus negative pi half, or pi half times 2. So 1 is equal to 2 times a squared over a cubed multiplied by pi. Okay, now finally we have to solve for a, right? So let's move everything over. So this is going to be a cubed over 2 pi is equal to a squared, which therefore implies that your normalization factor is a is equal to a square root a over square root 2 pi, or a square root of 2a cubed over pi, however you want to write it. Did I do that right? 2 pi at the bottom. Oh, I just realized. No, I did not do that, because I had a 1/2 here and I didn't move it over as a 2, so that's supposed to be 1/2. Okay, fudge the numbers a little bit, my bad. The 2 goes down here, the 2 goes down here. Okay, in that case, the 2 goes up to the top, so that means that it's a square root 2a over square root of pi. Okay, there we go. That looks more correct. All right, that is part A. Okay, part 2, now let's find the expectation values of x, x squared, and then find the corresponding uncertainty in x. So expectation x is just going to equal the bracket of psi of x comma 0 with x in the middle. Because there's no complex numbers here, it doesn't really matter. We can just order this as default. This is going to be negative infinity to infinity of a squared times x over x squared plus a squared, like that, squared. Taking the a out, right? This is going to be, what's that? That's like a squared times 2a over pi, so 2a cubed over pi. Let me just erase this real quick. Okay, 2a cubed over pi at the front, and then you have an integral from negative infinity to infinity of x over x squared plus a squared squared dx, and you should immediately see this is an odd function evaluated over a symmetric range, so because of that this is automatically equal to 0, so therefore the expectation value of x is equal to 0. Now let's move on to the expectation value of x squared. in which case we have the exact same setup, right? So 2a cubed over pi, integral negative infinity to infinity. This time it's x squared on top, x squared plus a squared squared dx on the bottom. Okay, and for the same reason, right, once again, we want to use trigonometric substitution because we have something that looks like x squared plus a squared on the bottom. I'm going to say that x is equal to, and in fact, let's do this in a different color so that we know this is the substitution work that we're doing. X equals a tangent of theta, in which case dx is equal to a secant squared theta d theta. Similarly, x squared plus a squared is going to equal a squared tangent squared theta plus 1, which is equal to a squared secant squared theta because of trigonometric identities, right? So now we plug in everything here. Expectation value of x squared, let me scroll down a little bit, is going to equal 2a cubed divided by pi in front, and then an integral. Once again, we plug in, just like we did for part A, the negative infinity into this expression to get that this is inverse tangent of negative infinity and inverse tangent positive infinity, which is respectively negative pi half and positive pi half of x squared, which becomes a squared tangent squared theta. The bottom, you get a squared, or let's just write it out fully, a fourth secant fourth theta. And then on top, dx becomes a secant squared theta d theta. Okay, now let's do some cancellation. A and a squared make a cubed. That's going to cancel at the bottom. So that's going to get negative pi half to pi half of tangent squared theta. A, secant squared and secant fourth cancel to make secant squared on the bottom, d theta. Let's move the a out and just cancel it with the a cubed on top. So the a goes away, this becomes a squared. So now we have 2a squared over pi times a d theta integral from negative pi half to positive pi half of tangent squared over secant squared theta. Now, remember that tangent is just sine over cosine, so sine over cosine multiplied by secant, which is 1 over cosine, right? So if you're dividing by secant, that's the equivalent of multiplying by cosine. So times cosine is going to give you sine. Squaring that is going to give you sine squared. So this simplifies to 2a squared over pi, integral negative pi half to positive pi half of sine squared theta d theta. Okay, at this point, we can once again use half-angle theorems, right? Because we know that sine squared, let me just write this in blue, sine squared of x is equal to, by half-angle theorem in this case, I guess, 1/2 1 minus cosine 2x, though half-angle and double angle are kind of interchangeable, realistically. So this is, we're going to use this identity for trig. We're going to replace this, and we're going to get 2a squared over pi times the integral negative pi half to positive pi half of 1/2 1 minus cosine 2 theta d theta, in which case the 1/2 cancels with the 2 and the front, and now you have a squared over pi, integral negative pi half to positive pi half of 1 minus cosine 2 theta d theta. This expression right here is going to equal theta minus 1/2 sine 2 theta, I think. Same thing, right? Cosine times 2, yeah, negative pi half to positive pi half. Once again, for the same reason as in part A, this expression is just going to go to 0 because sine of pi and negative pi is equal to 0. This expression right here is going to go to pi because pi half minus negative pi half, right? That's pi half plus pi half. Ultimately, expectation of x squared is going to equal a squared over pi multiplied by pi, which is therefore just equal to a squared. That means finally that the uncertainty in x, which is equal to the square root of x squared minus the expectation value of x squared, like that, is going to equal a squared minus 0, because we found that the expectation value of x is 0 from earlier, and this is just going to equal a, and that is part B. Okay, Part C is going to be where we actually encounter the required use of the contour integral and also the Cauchy residual theorem. It actually is going to result in what I would like to consider a canonical integral that you often, pretty much everybody taking a Calc 3 course would encounter very early on as sort of a typical challenge problem. So let's just start this. Find the momentum space of the function. So we just take the Fourier transform. Phi of p comma 0 is equal to 1 over the square root of 2 pi h bar. I'm going to take the integral from negative infinity to positive infinity, e to the negative ipx divided by h bar multiplied by psi of x comma 0. Close this with a dx. So now that we have psi, we plug in the a value at the front, right? So now we have a square root 2a over pi multiplied by 1 divided by square root of 2 pi h bar. And this is going to, let's see, the 2's cancel, the pi's combine, so you have a over pi multiplied by the square root of a over h bar. This is then being multiplied by the integral from negative infinity to infinity, now of e to the negative ipx divided by h bar over x squared plus a squared. Close that with a dx. And now you have something that's very close. Technically, the canonical problem is actually e to the positive ipx divided by h bar over x squared plus a squared. But these two are actually interchangeable. And I'll show you why. So if you convert this complex exponential into a sinusoid, right, e to the negative ipx divided by h bar is equal to cosine of px over h bar minus I sine of px over h bar. So this splits your integral into two expressions, right? One expression is cosine px over h bar divided by x squared plus a squared. The other one is negative I sine px over h bar divided by x squared plus a squared. This term is odd, so automatically an integral from negative infinity to infinity of negative I sine px divided by h squared divided by x squared plus a squared is just going to go to 0 automatically. So you can ignore it, leaving just phi of p comma 0 being equal to a over pi square root a over h bar times the integral from negative infinity to positive infinity of cosine px divided by h bar divided by x squared plus a squared. So the negative I px over h bar splits into a cosine and a sine. The sine can be disregarded because it's odd, leaving just the cosine term. And from here, there's nothing stopping us from saying, okay, I can rewrite this as p comma 0 equal to, copy paste everything here at the front. And then instead of taking this integral, I can say I can take the real component of the integral from negative infinity to positive infinity of e to the positive now ipx divided by h bar over x squared plus a squared dx. And this is the exact same thing as what I have up above. So now, instead of dealing with the negative ipx, I'm dealing with the canonical positive ipx over h bar divided by x squared plus a squared integral. Okay, now this is just going to be a Cauchy integral, right? And once again, this isn't a math course, this is a physics course. I'm not going to spend the an extremely long amount of time going over Cauchy residual theorem in depth. I'm just going to sort of very basically do sort of a general overview of how to do this problem. If you don't know any of the terminology or don't know what I'm talking about, I heavily recommend that you go and review your Calc 3, review contour integrals, review the residual theorem or the residue theorem, because otherwise you're not really going to understand how to actually solve this integral, right? So on a very basic level, Cauchy residue theorem is basically saying that, hey, if I have a complex function, I can basically do this, where if this is the real line, and this is the imaginary line, right now because I'm integrating over dx, my integral is effectively a line going this way, right? From negative infinity to positive infinity, or from negative a to positive a, or whatever you want. This integral If I extend it via a semicircle this way and create a line integral instead, this is now a line integral of my function f of z, right? Cauchy's residue theorem basically says that, okay, if I have some function and it has poles inside of my contour, in this case, this function right here has a pole at x equals plus minus ia, right? Because if you plug in x equals ia or negative ia, you're going to get negative a squared plus a squared, which goes to 0, so the function blows up. Here I have a pole at x equals positive ia, and theoretically I also have a pole at x equals negative ia, but we'll talk about that one later. But because I have a pole here, Cauchy's residue theorem basically tells you that, hey, this integral is actually equal to a formula which is equivalent to 2 pi times I times the sum of the residues of f of z, where the residue follows a different formula. And this specifically requires a counterclockwise. Let me rewrite. CTCQW. This specifically requires a counterclockwise line integral. So in this case, going in the direction of these arrows, right? And all this basically requires is for the function f of z to be differentiable over the complex plane infinitely, and this is, right? So the thing that you can connect to here is that if you extend this half circle out to infinity, it turns out that the part of the contour integral along the half circle just goes to 0 as the radius goes to infinity in polar coordinates. So because of that, this contour integral is actually exactly the same as just this real line integral. And to see this in more detail, let us take the actual factor of interest here, which is the e to the ipx divided by h bar, right? So if you have e to the ipx divided by h bar, if you convert this into sinusoids and whatnot, this is actually just, or not sinusoids, if you convert this into polar coordinates, we know that in polar coordinates, x equals r cosine theta plus I r sine theta, where, you know, this is my r, and then I have some theta, right? In that case, if I plug this into here, this becomes exp of ip over h bar r cosine theta minus p over h bar r sine theta. And now I have a term that is partially real and partially imaginary. Now, keep in mind that over here we said that the phi term purely depends on the real component. So because of that, since, you know, the real part and the imaginary part of a function doesn't really interact with each other, all we really care about is this term right here. This term, for all intents and purposes, can just be ignored, and we can just treat it only with the real expression. So I have a term here that is an exponential of negative p h bar r sine theta. And remember what we said earlier here, if we can get the semicircle part of this contour integral to go to 0 at infinitely far away, then what we have left is a contour integral that is basically only the bottom side, which is basically the real component of this integral. So then you can equate them, and you can set them equal to 2 pi I times the sum of the residues. In this case, for that to be true, we have this term of interest, which is exponential negative p over h bar r sine theta, right? And r is just a positive constant. H bar is a positive constant. So because of that, now what I have left as variables of interest is p and theta. Sine can obviously be positive or negative depending on if we close our contour on the upper side or the lower side. Because if we close our contour on the upper side in blue, then theta goes from 0 to pi, in which case sine of theta is always going to be positive. Now, alternatively, if we close our contour from the bottom side, right, in that case, pi less than equal to theta less than equal to 2 pi, in which case sine of theta is going to be negative. Which direction we close is ultimately going to depend on the sign on p, because if p is always positive, then remember our requirement is that this negative is retained. So if p is always positive, then we want sine of theta to also be positive, in which case we close on the top half. If p is negative, then the two negatives cancel out. We have to get a third negative with the sign of theta, in which case we close on the bottom half. And just to emphasize here, the red side is clockwise, like that, right? Because once again, you're integrating from negative infinity to infinity, so it starts always from the left to the right, and then you close the contour with the semicircle. And that is sort of the problem that we're going to end up with, is that we're dealing with momentum for p, and momentum can be positive or negative, so because of that you're dealing with two situations here. So we're going to have to treat each one separately. So let's consider the case 1 where p is greater than 0. If p is greater than 0, then in that case p here is always positive, right? That means that sine theta always has to be positive, which means that we're closing in the upper hemisphere. So because of that, we're going to get that the residuals at z equals positive IA, because that's where, here, let me just draw out this graph again, actually. This is the real line, this is the imaginary line. We're closing on the upper hemisphere. And the reason why is because we want this exponential to go to 0 when r becomes infinitely far away, so that way we can apply the residue theorem. So now we have to calculate the residue, because this function has a residue at z equals positive IA, right? So the residue at z equals positive IA is going to equal the limit as z approaches IA of z minus IA times the function, which is going to be e to the positive IPx divided by h bar, or in this case x is getting replaced with z because now it's a function of z, because it's a complex function now, or we're treating it as a complex function in the complex plane, and then we get z squared plus a squared. Now we can then just replace this, right? We can factor this and get z plus IA, z minus IA, in which case this one cancels with this one, so you're left with this limit as z goes to positive IA of e to the IPz divided by h bar over z plus IA, in which case this ultimately equals e to the IP times IA divided by h bar over 2IA, which is equal to e to the negative PA over h bar divided by 2IA. Now plugging this into our Cauchy residue theorem, right? Our contour of f of z, and remember this has to be counterclockwise, CTCW, dz is equal to 2 pi I times the sum of the residues. There's only one residue, so times e to the negative PA divided by h bar divided by 2IA, in which case the two i's cancel out, you're left with pi over a times e to the negative PA divided by h bar. Okay. Now let's consider the second case, where p is less than 0, in which case we now, in order to ensure exponential decay as r goes to infinity, we are going to have to close on the bottom half. So this is the real component, this is the imaginary component. This time we are going left to right and then closing on the bottom half like this, in which case our new residue is at z equals negative IA, in which case our residue is going to equal the limit as z goes to negative IA, this time of z plus IA, multiplied by e to the positive pz divided by h bar divided by z plus IA, z minus IA. The plus IA's cancel out like that. What you're left with is limit z goes to negative IA. Whoops, left out the negative. of e to the I p z divided by h bar divided by z minus ia, in which case this is going to equal e to the ip times negative ia divided by h bar divided by negative 2ia. Writing this out fully, this is e to the power of the two negatives cancel out, make a positive, so pa over h bar divided by negative 2ia. Now, plugging in to the contour theorem again, the contour integral of f of z about counterclockwise is equal to 2 pi I times the sum of the residue, which is e to the pa divided by h bar over negative 2ia. The two i's cancel, leaving negative pi over a, e to the pa over h bar. Now, the key point here is that this is a counterclockwise integral. This line integral is clockwise. So to turn it counterclockwise, we have to add a negative 1. Or to turn this clockwise, we have to add a negative 1. So the negative of the integral that's clockwise of f of z is therefore going to equal pi over a e to the pa over h bar. And this is what equals the counterclockwise one. So to switch from counterclockwise to clockwise, we have to add a negative 1 at the front, right? So now we have what's basically our integral, right? Because we've equated the integral now. This means that phi of p comma 0 has two scenarios. It is going to equal, and what was our term at the front again? Let me just copy that over. And remember, once again, we only care about the real component, right? The imaginary component of this expression, the IPH bar r cosine theta, that might explode or behave weirdly, but we don't care about it. We only care about this component. So because of that, we can just do this and only care about the real component. In this case, however, it does look like doing it this way basically causes the imaginary component to disappear anyway, so I don't think it mattered in this case. But even if it resulted in some imaginary attachment here, you could just get rid of it, because once again, you're only looking at ultimately the real component of the integral, right? So this is going to equal this thing at the front and then multiplied by either e to the negative pa over h bar in the case where p is greater than 0, or e to the positive pa over h bar in the case where p is less than 0. Now, if you look at this, if p is greater than 0, this is, you know, a and h bar are both positive, so this overall term is now negative if p is greater than 0. If p is less than 0, the overall term is once again negative. So what basically we require is that no matter what, regardless of if p is greater than 0 or if p is less than 0, it has to be negative. And one way that we can reconcile this and turn this into a single equation is if we used a magnitude p instead of just p. So this is equal to a over pi times the square root of a divided by h bar. And now we can just do e to the negative magnitude p a divided by h bar. Because if I do this now, regardless if p is positive or negative, it's always going to be positive here, and I have the negative sign at the front conserving the negativity of the exponent. And that is our phi. Now let's check for normalization, right? So if this is our wave function in terms of p, then our magnitude squared is going to equal a squared over pi times a over h bar, right? Times the integral of, actually, wait, hang on. Actually, no, sorry, I just realized there's a pi over a at the front here in both cases. So actually the pi over a cancels out with these two, so the pi over a disappears. So in that case, the magnitude squared is now just a over h bar, and I want to write that in black, not blue. A over h bar times e to the negative 2 magnitude p a divided by h bar dp. So in that case, we can once again split this into two integrals to get rid of the magnitude term. So this is equal to a divided by h bar. This is from negative infinity to infinity. So we can divide this into one integral from negative infinity to 0, where p is always negative, and the negative here has to be retained, and ultimately the p here is going to come out as positive. So we can rewrite this as exponent 2pa divided by h bar, because since p is going to be negative anyway, we can retain the negative sign here by just getting rid of it at the front here. Close this dp, and then add integral from 0 to infinity e to the negative 2pa over h bar like this, to preserve the negative sign here, because p is always positive on this side. In which case, if we do this integral, this is going to be h bar over 2a e to the 2pa over h bar, going from negative infinity to 0, plus negative h bar over 2a e to the negative 2pa over h bar, integral 0 to infinity. Okay, I can factor out an h bar over 2a, so a over h bar times h bar over 2a. And now I have e to the power of 0, which is 1, minus e to the negative infinity, which is 0, subtracted by, I think that's 0, yeah, e to the negative infinity is 0, and then that becomes minus 1, like that. So that becomes a cancels, h bar cancels, 1/2 of 1 plus 1, which is equal to 1, therefore normalization is conserved, and we are done with part C. Okay, part D, use the results from part C, calculate the expectation values of p, p squared, and finally find the uncertainty of p at time t equals 0. So we have phi of p comma 0 up at the top here. Expectation value of p is going to equal just a over h bar, integral from negative infinity to infinity, p times e to the negative 2 magnitude p a divided by h bar dp. And this term is odd, right? Because this expression here, this is the p of power 1, and this is just an exponential factor. So because of that, this automatically goes to 0, since it's a symmetric integral about an odd function, in which case p squared is going to equal a over h bar, integral from negative infinity to positive infinity of p squared e to the negative 2 magnitude p a over h bar dp. And this, in this case, is even now. So if this is an even function, then this is equal to 2 times a over h bar integral from 0 to infinity, where I'm just doubling it because it's symmetric about the y-axis. So this is equal to p squared e to the negative 2. You can get rid of the magnitude p, because p is always going to be positive now, since you're going from 0 to infinity, times a divided by h bar dp. And now we can just use integration by parts, or u sub in this case, and say u is equal to p squared, in which case du is equal to 2p dp. dv is equal to e to the negative 2pa divided by h bar dp, in which case v is going to equal negative h bar over 2a times e to the negative 2pa divided by h bar, I think, because if I integrate by p, that gets a negative 2a over h bar, and those cancel. Yeah, so that becomes uv minus integral v du. So this is equal to 2a over h bar multiplied by uv, which is p squared times negative h bar over 2a e to the negative 2pa divided by h bar, going from 0 to infinity, minus integral of v du, which is the minus cancels out with the minus here, makes a plus, h bar over 2a, integral from 0 to infinity of e to the negative 2pa divided by h bar times 2p dp. Now, this left term here, you have a p squared that goes to infinity, and you have an e to the negative 2pa over h bar, which goes to e to the negative infinity, right? So at 0, obviously it's 0 times like negative h bar over 2a, which is just 0. At infinity, p squared goes to infinity squared. E to the negative 2pa over h bar goes to e to the negative infinity. E to the negative infinity goes to 0 way faster than infinity squared goes to infinity. So because of that, the exponential term here dominates, and because of that, ultimately, this expression goes to 0. So because of that, you can get rid of it and say Okay, I'm left with 2a over h bar multiplied by h bar over 2a, multiplied by the 2 that I'm going to take out, and then multiplied by the integral from 0 to infinity of p times e to the negative 2pa divided by h bar dp. Now let's do some cancellation here. The 2 cancels out, 2 remains, a cancels out, h bar cancels out. I'm left with 2 integral from 0 to infinity p e to the negative 2pa divided by h bar. Okay, now for the same reason, I'm going to once again use u sub. U is going to equal p, du is going to equal dp, dv is going to equal e to the negative 2pa over h bar dp. I forgot to close the integral with the dp here. In which case v is equal to negative h bar over 2a e to the negative 2pa divided by h bar. Okay, doing the same thing, this is going to equal 2 times uv, which is, let me switch back to blue, p times negative h bar over 2a e to the negative 2pa divided by h bar from 0 to infinity, minus integral v to u, which is plus h bar over 2a, integral 0 to infinity, e to the negative 2pa over h bar dp. Okay, for the same reason here, you have a p and you have an e to negative. So p goes to infinity, e goes to negative infinity, or e goes to e to the power of negative infinity. So the exponential dominates the p, in which case this term just goes to 0. So I'm left with expectation value of p squared is equal to 2 cancels out with 2 at the bottom, h bar over a, integral from 0 to infinity, e to the negative 2pa divided by h bar dp, in which case this is equal to h bar over a times negative h bar over 2a e to the negative 2pa divided by h bar from 0 to infinity. This term right here is at infinity, this is e to the negative infinity, which is just 0, subtracted by 1. So the negative 1 cancels with the negative out here. Ultimately, the expectation of p squared is going to equal h bar squared over 2a squared. Okay. Now, let's actually find uncertainty in p, which is going to equal the square root of expectation p squared minus expectation p itself squared. This is square root of h bar squared over 2a squared minus 0, as we found earlier, in which case this is equal to h over a root 2. Okay, and I don't even have to do a jump cut now because for part D, I think it's just, I mean, for the final part, part E, we're just being asked to verify Heisenberg uncertainty principle. Let me just paste it over. Right, check that the Heisenberg uncertainty principle is verified for this state. So we have sigma p and we have sigma x from the other expression earlier. So we have, whoa, what is happening? Erase that. Okay, I think I messed up my color palette somehow. That's fine, let's just ignore this. We have sigma p is equal to h bar over a root 2 from part D, and then we have from, I think, part C, or is it part B? I forgot. But from one of the earlier parts, that sigma x is equal to a, in which case the product, sigma p sigma x, is equal to h bar over a root 2 multiplied by a, which is equal to h bar over root 2. And that is indeed greater or equal to the minimum value, which is h bar over 2. So therefore, the Heisenberg uncertainty principle is in fact satisfied for the state, and we are done with this problem.